We've talked about raster data, and raster data includes a whole variety of data sets that fall into the general category of remote sensing. Remote sensing is the opportunity to take pictures of the Earth from platforms, sensors, and then in GIS we can convert that information into data that can be brought to your maps. Just as a quick review of the concept of resolution. Here we've got an urban setting here, and you can see how the resolution properties lead to differences in the level of detail that can be perceived on the imagery, and also that can be analyzed. So in this example, we've got something like 10-meter data here, more like 30-meter data here, more like 80-meter data here, and these represent different generations of Landsat satellite data that you'll be able to work with in the labs that accompany this lecture. Remote sensing can be divided into active and passive modes. Active sensors are things like radar and LiDAR that emit energy from the platform, from the sensor. Here it's shown as a satellite, but it could be a drone as well, or it could be an aircraft. The aircraft or the drone with the satellite cameras put an energy pulse to the Earth and measure its reflection, and that allows for a lot of properties of the remote sensing data that we like, such as penetration of clouds with certain wavelengths and high resolution. Passive sensors, shown on the left here, use radiometers as their cameras, and those measure the reflectance of energy from solar incidents. So the sun shines on the Earth and the results go back to the sensor for recording into an image. Those results inevitably involve interactions with the Earth's materials, such as vegetation and built infrastructure. The illustration here of a Sentinel-2 satellite mission shows how we have, conceptually here, how we have multiple bands of information. We'll talk more about what that means in a moment. But for passive remote sensing, this is a good cartoon because it shows the power coming to the satellite, the camera on the bottom of the satellite here, as it were, and this is a swath that's coming around the near polar orbit of the satellite. These orbits take images continually, even though there might be clouds underneath, and so managing clouds as part of the methods of remote sensing is something that we've got to be very sensitive to and aware of. There are other satellites, and this constellation of remote sensing satellites here shows how many there are conceptually that are using different orbits and different systems for acquiring imagery of the Earth passively from solar incidents. Landsats 1 through 8, ESRS spot image from the French satellite company SpectralImagery have 1 through 7 satellites here. GOES, GERS is the Japanese, Sentinel, RadarSat from Canada, CSAT, and most of these have specifically tuned sensors to look at certain wavelengths. So we talk about wavelengths as units of the spectrum, and there are many graphics. I like this one because it kind of brings it all into one graphic. I've gotten these off various web resources. The interesting thing about this from the human standpoint is that what we can see as visible light around 1 micron of wavelength is a very, very small segment. Our eyes are adapted to just this small segment here. We're going to look more into what that wavelength is, that range of wavelengths is for visible light. So we see visible light, but there's also to the right of this are a variety of infrared wavelengths here, microwave wavelengths, and radio waves. And these radio waves can be very, very long, from meters to tens of meters to even kilometers of wavelengths, and they're very low energy. On the other side of the spectrum, if we get more energetic, shorter wavelengths become ultraviolet or X-rays, and the shortest and most energetic of all are gamma rays. And gamma rays are what are emitted. If anyone saw the movie Chernobyl, the meltdown that was happening was emitting invisible gamma rays at very, very high energy that, of course, caused a great deal of damage to all the people who were in the way of those very high energy waves. Just to bring a little bit more comparison of the trade-offs between passive solar, and in this case, active radar sensors. Synthetic aperture radar SAR satellites have the ability to cover very large areas. They can image at day or at night because they're adding the energy onto the ground, so they're not reliant on the sun. Unlike optical satellites, which are passive, they have typically high resolution but are dependent on sunlight and are more typically easy to colorize in the way that we're kind of familiar with our own eyeballs of looking at the landscape around us. Synthetic aperture radar is often used in marine environments, partly because it can see through clouds, or many of the wavelengths can, and also can be very sensitive to textures on the surface, such as sea textures. So there are different sources. We're not going to do much more. We're not going to do anything more with synthetic aperture radar, and we'll talk about active remote sensing later when we get into LiDAR data in a subsequent module. Here's an example of the Intel applications trying to, as they say, detect the signal of certain, or signatures of certain characteristics of the Earth, or the characteristics in this case of military infrastructure. So this is showing submarines and submarine infrastructure here, awnings and docks, and this is the radar imagery. Well, radar imagery can sometimes see through materials, so they can actually penetrate some of the awnings that the various countries use to obscure their infrastructure from being visible from overflying satellites. And in this case also they can change the energy angle, so they can basically point the satellite to come in kind of under the awnings at a low incidence angle. So it's hard to look at, but experts at this can get a lot of information out of this kind of active remote sensing in the Intel world. There's also thermal remote sensing. This is a type of passive remote sensing which is detecting some of those longer wavelengths I showed in the spectral slide a few minutes ago as variations in surface temperature. So in this case, we're looking at an area that's been warmed up by underground coal fires. And so bright is high temperature, lighter tones, and dark is cooler temperatures or colder surfaces. Now there is a lake here, and so the lake is warm because this is a nighttime image, and so when the ground surrounding the lake cools down at night, the water can hold heat, so you get a little extra thermal bloom. And water detection is one of the principal uses of thermal remote sensing for looking at, in agriculture, for example, looking at leaks in irrigation infrastructure. So there are lots of applications of thermal in addition to the ability to look at soils and agriculture. Thermal information is often used in climate change, volcanology, geology, forest fire management, intel and military areas. It's used a lot nowadays. Lower flying drone thermal images are used in search and rescue operations as well to be able to identify people from their heat signature. Now, there's a lot of vocabulary, and a lot of the words have very specific meanings that are not particularly intuitive, but you'll get to know them as we go through this course. And so I won't stop and define every term in this course, but I would recommend that you go click through and look at this glossary and have that available to you when we're doing labs and talking about things in class. As always, if you have a question about a term, I want you to bring that up. Please ask your questions, because that's when it's time to learn them. When you see context and it's not clear to you, that's when the learning will sink in. If I just describe what a polar orbit is now, for example, or a sun-synchronous orbit, it won't mean anything to you until you kind of need to know that. So use the glossary, learn the terms, ask about them. Let's have the discussions when they come up. I talked about gamma imagery, and so this is a drone that had a gamma camera on it, essentially a gamma detector, and it could create a gamma image of the radioactivity, essentially the gamma ray radioactivity coming off the Chernobyl infrastructure. And this is done in 2020, and of course we know that Chernobyl happened in 1986, so this is a way of doing continual monitoring, looking at radiation hotspots, and being able to understand how that relates potentially to public health and other implications. LiDAR, as I mentioned, laser imaging, detection, and ranging, is an active remote sensing model. This is an area right near Olympia where the Olympia Ecosystems is doing habitat restoration of a former dairy farm. Many of you have seen or been to that property, and some of you, I think, are even doing thesis work in that property. Well, here's what the property looks like from a LiDAR point cloud. And the LiDAR, again, it emits lasers onto the surface, measures the laser response time to turn that into maps of elevation change. So this is, you can see here the elevation is high where it's red and low where it's blue in this particular rendering. And this is showing a lot of tree cover, but also a lot of terrain variation and some infrastructure here around the old farm. And so it creates a very lively, very high resolution, very versatile image of the Earth's surface, but only typically over fairly small areas at a time. And I'm learning more about using LiDAR data in cartographic applications. This is taking 9 frames, so you can see from back here, you can't really see, but there's several LiDAR frames that are mosaic together. These are 9 frames that are mosaic together that create one logical LiDAR image, and then we can use various cartographic methods to generate surfaces from that and pseudo-color the surfaces. And if you look closely in here, you can see some of the former Deschutes River channels here running along inside the green area here. Those are tiny variations in elevation of former channels and oxbows and things where this river has changed course over the years. And you can also get a sense of that here in this wetland area. So this has on it also the parcel boundary of the Olympia Ecosystems lands that they're using, which is a little bit confusing. But we'll do some work. If it's interesting to students, we could put this together as a lab for how to do raster cartography with LiDAR. Now we're going to focus now mainly on the passive version of remote sensing and using the visible near infrared. So here's another jargon term, or the visible or very near infrared is the spectrum that we're mostly concerned with in passive remote sensing. Not to say there aren't, as we know, applications in thermal and other wavelengths, but most remote sensing that's used in GIS is coming from this electromagnetic spectrum that is in this range here, not gamma, X-rays, ultraviolet, not infrared radar and AM radio, but in this visible light spectrum that goes from basically 4 times 10 to the negative 7 microns, or meters rather, so which, you know, you're going to have different units here. I like to refer to it as 400 nanometers. We'll talk about units in a moment. But this is blue and purple light here. At one end of the spectrum, we can see green light around 500 to 600 nanometers. We can see red light around 700 nanometers, and then our eyes really stop being able to see here. But there's also some very near infrared that's very important for plants. And so again, there's a lot of jargon here. We might refer to that as VNIR, very near infrared, or short-wave infrared. Those are all terms that are used, terms of art that are used somewhat synonymously for this range that's just more red than we can see at 700, but as you'll see, has important properties for plant detection. So there's the visible spectrum from 0.4 to 0.7 microns, or 400 to 700 nanometers. And plants, as I mentioned, have a reflection in the shortwave infrared spectrum that's just a little bit longer than our eyes can detect. Now, let's talk about how other Earth surface interactions affect the signature, as we refer to it, of the landscape. The signature is a term that remote sensors use for describing how the image is constructed from reflections off specific parts of the landscape, of the ground, or of the surfaces that the light is being detected from. And we often refer to those as pixels. You saw that in the first slide. Resolution has to do with how large the area of detection is, 10 meters, 30 meters, 80 meters, or maybe if you're doing LiDAR imagery down into inches. But in any event, the landscape reflects solar energy from the passive energy source of solar energy, and each of these surfaces contributes a different property to the reflected imagery. So, for example, water is highly absorptive in many wavelengths, but it does reflect in some wavelengths. Plants reflect, as we were just talking about, in green. That's why we see green when we look at plants, healthy plants like grass or deciduous forest trees, and absorb in other wavelengths. And they're often very bright reflections of all wavelengths off paved surfaces like paved roads or rooftops. So being able to distinguish those is part of the challenge of remote sensing. Now, let's see. I think we've basically covered this already, but I do like this because there's a free remote sensing book you can acquire here. I haven't checked that link lately, but I have gotten that book, and I think I got this picture out of that book from that website shown there below. This is just another picture of the same story we've been telling about how our visible detection is very limited to sort of the middle of this range of high energy to low energy, short wavelength to long wavelength energy. So now, in order to be able to detect the energy, the sensors are designed to collect ranges of energy in different bands. So we refer to the bands, this is in this case the typical bands of many remote sensing platforms. Now again, there are variations depending on the platform, but most remote sensing platforms that you'll work with in GIS at least have detection in the blue, the green, and the red, and the near infrared or very near infrared range of spectral response. Blue is 440 to 500 nanometers, or 0.4 to 0.5 microns. Green, 0.5 to 0.6. Red, 0.6 to 0.7, give or take. And again, there are variations here in the fine print of how engineers construct these bands to perform the purposes, to achieve the purposes of the remote sensing platform. And you can see what some of these purposes are here. Blue is good for looking at deep water imaging, and the blue wavelengths can actually penetrate the atmosphere in some water, as in they can sometimes go as deep as 50 meters in clear water to detect the bathymetry, or the bottom of shallow bodies of water. Green is typically used in vegetation. Red is typically used for looking at man-made objects and is also important for comparing to green for vegetation purposes. Near infrared is about vegetation because these wavelengths here have a strong reflection from plants. We'll talk more about that in a minute. Other longer wavelengths are used for soils, for some fire monitoring. As we mentioned here, heat. This is the area where you might do search and rescue and be looking at nighttime studies of the comparison of water bodies or irrigation leaks to the surrounding landscape. And microwave gets us into radar here. So here's another picture of that chart. So here you can see, let's look back at the chart. Blue is 0.4 to 0.5 microns. So here you can kind of see how that's from 400 to 500. This tall blue response here is showing how the detectors are organized to make a detection for blue, or in the case of green, at 500 to 600, this green shoulder here, or in the case of red, this red one here. Here's the very near infrared at 800 to 1,000 nanometers. And that's, again, beyond what we can see. And then the sensors also can determine other longer wavelengths for other purposes. So you can read more about this. This is the Landsat 8 satellite system and is a very common source of imagery that's used, available for free around the world thanks to NASA, and the longest remote sensing platform in continuous operation in history, which is the Landsat platform. Now, looking at that same chart, so again, we went from this table that talked about the wavelengths that are involved. Now we've turned that on its side to look at this chart that symbolizes the response, the sensor detections, and how the sensors are designed to detect response in these spectral areas. Strong response is up here, and then these areas in between response, or where there's no detection. And often those are because water absorbs very strongly in those areas, so you really can't get much off the land surface because of the interference of water absorption. So there's no reflection. Now, let's look at the area of blue, 0.5, which is really green here, to roughly 1 micron, or 500 to 1,000 nanometers. And now we're looking at the typical spectral response of surfaces of materials that are part of the Earth's landscape as they interact with solar radiation. They perform in different ways. So let's look, for example, at snow. Snow is going to be bright in the blue. It's going to be relatively bright, but not quite as bright in the red, and there's going to be a fall off here. So that's a spectral response of snow. Now that's completely different than the spectral response of, say, irrigated grass, shown here in blue. Irrigated grass has a little peak here in the green, which we expect because we see irrigated grass as green, an absorption here in red a bit, and then a massive response here by comparison, a very significantly higher reflection in a wavelength that we can't see, that is in this very near infrared area, that's longer than 0.7 or 0.8 and as long as 1 micron or 1,000 nanometers. So if we could get a sensor that can detect the very near infrared, longer than we can see, but still very responsive to vegetation, then we can compare how the response of the Earth's surface is in these different wavelengths, and use that to detect things like where is the irrigated grass as compared to the coniferous trees, as compared to the deciduous trees here that have not as high as irrigated grass a response in the very near infrared, but still a very strong response compared to coniferous. And concrete cement here is kind of interesting. It's just kind of flat, right? So when we don't see much variation across the spectral bands, things tend to turn out on the imagery as kind of shades of gray, and we learn to detect that signature as built infrastructure. So here's looking now at the spectral response of grass, the spectral signature of grass, as the green line running along through here. So this is just taking that last picture now and kind of sandwiching it together with the engineering picture of the response curves of the detectors that are shown here in these blocks of color. So let's review what spectral signature of grass involves. It's low in blue, higher in green, lower in red, very high in near infrared. So that's this distinctive grass curve of spectral response. Now that assumes the grass is well watered and it's in its metabolically active phase. It's not dead of winter. This would be springtime or summertime grass in a setting that's allowing for very active chlorophyll metabolism. The sensors are going to detect blue in this range. They're going to detect green in this range here. So you're going to get, all across the screen, you're going to get the detection of that little green rise in reflectance. They're going to detect red here, and then the very near infrared is going to have this detection of this plateau of high response at 0.8 to 0.9 microns. And there's a subgrouping of the very near infrared. It's called red edge, which is just past what we can see at 0.7 microns or with our eyes, but at 0.75 to 0.8 microns is a red edge detector. So these are, let's see, these tell you over here what the different systems are. For example, enhanced thematic mapper band 1, enhanced thematic mapper bands 1, 2, 3, and 4. So that's not as important because these different sensors are designed in different ways. But what's interesting or important to know here is that the engineering of these detection sensors is constructed to match with the typical responses of materials that people want to create maps from. Now, as I said, that's assuming that the chlorophyll is actively photosynthesizing, that there's an active, an abundant chlorophyll pigment in the vegetation that's absorbing blue and red and reflecting green light and reflecting also in the very near infrared. So here we see a, excuse me, we see red, green, and blue light coming in and green coming off. Now this is coming from the side. You know, from passive remote sensing, this arrow would be pointing from up above, but just in principle here, the red and the blue are absorbed and the green is emitted. And that's what we can detect. And the same thing happens with infrared coming in and infrared being emitted as well. Solar infrared versus the high signature that we're seeing here in this 0.8 to 1.2 micron area of plants that are reflecting in that range. When the plant changes, as in senescence or disease, or just happening in the autumn when the plant's chlorophyll shuts off, other pigments begin to appear. Why do plants look? Why do we love those fall colors? Plants looking orange and red. Well, because there are other pigments. There are carotenoids and other pigments that are in the leaf that are allowed to be observed reflecting at their lower levels when the chlorophyll is dead. So when the chlorophyll is no longer reflecting, then the other pigments can come out, and we see that as fall colors. But we can also see here how this is simulating here a healthy leaf. So you've got low blue, high green, low red, high near infrared, as opposed to a sick leaf, which has less distinction between those, as opposed to a dead leaf, which is sort of flat, all about the same, because the chlorophyll and the leaf tissues aren't reflecting as vividly, as brightly, as energetically. They're not reflecting in green and near infrared. The sensors can, now this again should be a spacecraft pointing down, but if you just turn the system on its side, what we're seeing here is a detector system here, and there's a term called push broom sensors, but if you go back to that original picture of Sentinel-2 and its swath across the Earth from pole to pole, it's detecting all the time, and it's as though it's pushing a broom across the landscape to create these strips of imagery here. So the object gets brought into the sensor. There's a dispersing element, think of it as a prism, that then refracts the energy from the solar incidence interacting with the object, such as a tree, into its different wavelengths. And then those wavelengths get picked up and recorded, and that's where we get these different bands from. And you can see here the RGB, right? The red, green, blue bands, as well as these infrared and thermal and other bands here that are very near infrared and shortwave infrared, and other bands that are not visible to our eyes but can still detect, can be used for detection of landscape properties on the ground, on the landscape. Okay, so we've talked a little bit about bits and bytes in elevation models. Let's talk about it here in terms of imagery. Here's an 8-bit image, so it's a grayscale image. There's one gray channel here, and you're allowed to have in an 8-bit image 2 to the 8th possible values of gray gradation on the image to be displayed on the monitor that we have. The typical monitors that we have are 8-bit monitors. Now they're actually called 24-bit monitors. We'll come to that in a moment. But in gray image, we can have 256 gray values to get a sense of texture and perception and contrast and comparison of different properties of this image, from a straw hat to a cloth of some kind here, to walls, to skin, to eyes and hair, and all these things have different spectral responses. And we can see that as grayscale image in an 8-bit image. Now, if you put 3 8-bit images together, one for red, one for green, one for blue, then we can display that on our RGB monitors with 256 times 256 times 256 possible colors. So now with 24-bit imagery, 3 8-bit images, one routed into each color channel of our computer monitor, we can see a great deal more distinction here. We can see many, many more subtleties of color and shading because we've got up to 16 million and some possible colors. Landsat imagery has a footprint, as we refer to it. So here's the footprint of some imagery of Monterey. This is the image, by the way, you'll work with in the coming lab. The The satellite direction of flight is from north to south, coming down the middle of this image. So it's not true north-south, it's offset from north to south. Well, it would have to be so that it can, the orbits are calculated to allow for an orderly, consistent acquisition of imagery over the entire Earth's surface. So, but the result of that is that these images are sort of tipped. And so they chunk up the swath into image, which are called columns and rows or scenes. And so here's a Landsat imagery footprint that is, because it's a raster image, you see where the hand is here. The hand's here on Monterey Bay, but just to the left of it is an area of no data. So this area of no data has to be there to sort of pad out the rectangular data structure of rows and columns that we talked about in a previous lecture. Raster data is based on having a consistent number of rows and columns across the image. So what do you do when you've got an area of no data that surrounds an area of valid data, as in this very typical Landsat scene? Well, we can give it a no data value, and so here's the ability to display, or rather not display, the background value, which in this case is 000, and that turns into an image where now you can see the base map, because we've instructed those triangles around the edge of this are still in the raster data, but we've given it the instruction here to avoid displaying that so that we can see other layers, and we're not obscuring the other layers with the padding around the area of valid raster data. So that's the no data value, the no data condition. 000 can be used. Other numbers can be used here as the no data condition. When you looked at elevation models, we saw one elevation model that used -99999 as the no data condition. So it's part of the metadata to tell you what the no data condition is and how to then tell the software how to handle that to allow the background to show through those otherwise obstructing triangles of black that surround the area of valid raster data. Esri in ArcGIS Pro provides a wide and growing variety of raster functions. So here in this cartoon, the raster functions are shown here as this kind of gear set, right? Function of X. And X is coming from the source rasters. And so these might be 1, 2, 3, 4, 5, 6, 7, 8 bands of Landsat imagery, for example, here. They're being routed into a function, and then the function generates temporary output layers, and then those can be used as layer files in your map. Those can also be exported into your geodatabase. And so raster functions are a very efficient, very agile way to conduct rapid analysis of imagery in the Esri system. They work on the screen extent. So for example, if we look back at this particular image, suppose we're interested in just this area here. This is a little wetland area called Moss Landing. So suppose we're really interested in the natural area around this wetland. Well, with raster functions, we can zoom in on that, and then it will perform the functions just on the area that's in the display list. So it doesn't have to go read the entire image, and that can be a very time-demanding and inefficient process that is solved through the use of raster functions. And you can read more about raster functions here, and I recommend you follow through on these links that are here and that are hot linked in this slide presentation. For example, that hot link brings up this content. Here are lists of raster functions here, many of them, as you can see here, and each of these has its own ability to click through. For example, we can look at what we'll look at in a moment here, the NDVI function, Normalized Difference Vegetation Index. We're going to talk more about that in a minute, but just realize that you can click through to this web page and you can get help on all of these functions and how they work, and that's important and valuable reading for those who want to do more with remote sensing. So there's the list of raster functions again from that web page. Let's talk about NDVI. NDVI is the Normalized Difference Vegetation Image. It's a very common raster function applied to 4-band, at least, remote sensing imagery. The bands that are necessary to conduct an NDVI are the red and the near infrared. and it's the contrast between red and near infrared that allows for the detection of healthy vegetation using this rapid computation of a light equation here in the NDVI index. So healthy vegetation, as we saw, absorbs most of visible light and reflects a lot in near infrared light and of course in green. Unhealthy vegetation reflects more in visible light and less in the near infrared. So the NDVI image is based on the use of the near infrared. So you take the near infrared value at each pixel and subtract the red value, and then you divide that by the addition of the near infrared value and the red value, and that gives you this index. And it's a simple equation, and in the lab you'll do some actual computations of that from pixel values. Keep in mind, you cannot do this with just any band. You have to have the near infrared band and the red band. And I guess we could run back. Oh no, we're going to do that in the next slide here to show, just to remind you how that works. But basically, NDVI can measure the sort of greenness, the chlorophyll density that's present on the plant, in the plant, and in the photosynthetically active region of the spectrum, plants use the wavelengths of blue and red to create sugar from the inputs of water and carbon dioxide and sunlight, and also generate oxygen as part of that process. So that's the photosynthetically active process, and in that spectral region, photosynthesis causes the absorption and reflection, absorption in certain wavelengths and reflection in others. Now, plants also reflect in the near infrared wavelengths because they're trying to shed the damage that can be caused by heat. So, why would plants let any? They need the photosynthetically active region, which is 0.4 to 0.7 microns, in order to conduct plant metabolysis. But they don't need longer wavelengths, and those longer wavelengths could cause damage to the cell. So that's why we have this high reflection in near infrared. And those often come from the tissues around the outside of a plant leaf, for example, that are trying to protect the photosynthetic cell structures inside the leaf. So we're about to get into like a discussion of the light anatomy of plants, and that's a deep topic, and there are research papers about it. They're quite fun to read, but we don't have to know all that to be able to use the imagery from this. Vigorous plants are absorbing and in the 400, 700 nanometer region, but they're reflecting in the 800 to 1100 nanometer region. So that's why we want to have this comparison between the absorption and reflection extremes to construct the NDVI equation. And so to look at that again here, we've got chlorophyll absorption here at, in this case, showing here in the 0.6 to 0.7 area. We've got reflection here in the 0.5 area, which is green, absorption in red, and then we've got high reflection here in the very near infrared. So that, again, this is this comparison. So if you can compare what's happening in this area to this area using this NDVI equation, then you can come out with a map of that. Just to bring home the difference between healthy and unhealthy or senescent vegetation, here you've got a nice kind of cartoon of this from EOS, Earth Observation Systems.com, about NDVI. And there's lots written about NDVI. If you click through on this, you'll get some pages here to read about NDVI. But here we've got near infrared and a strong reflection of that, and visible, a strong reflection of green. But generally absorption here, so that only a small percent is reflected in the infrared. Let's see. That's right. So this is where the NDVI is high, 0.6 and up. We have this pattern of reflection and absorption. Where the NDVI is lower, these values are closer to each other. There's more reflection of infrared off the tree here and less reflection of near infrared. that infrared visible really should be red. I think is what we're talking about here. The infrared visible is actually red light. Sorry, so let me just rephrase that. Very near infrared is strongly reflecting. Red, infrared visible, is absorbing only 8% reflection. On a dead tree, there's more red reflection and less near infrared. So that's why we can get a different NDVI value. So these raster functions here, well, you've already used raster for contouring, for example. And you might recall that when you did contouring on an elevation model, the results were stored in the display list in the display memory of the project, not in the geodatabase. But that's why we also ran geoprocessing as a contouring as a geoprocess, so that stores the results in the geodatabase. You have to be cognizant of the trade-offs between slower but storing the data through geoprocessing versus faster response but not storing it, but you can still use it for cartography and maps and analysis from the raster functions. So here's an NDVI output range. The output range is using what's called scientific values, and the scientific values range from 1 at the high end of bright response, and you can see that occurring here in these center pivot irrigation areas, to -1. This dash over here is badly placed. It should be -1 to 1. So the negative ones are going to be these areas of kind of colorized, symbolized as browns, where you've got kind of a mineral surface. This is a desert agriculture setting, as you could probably imagine. And in the desert agricultural setting, where you've got lots of sunlight and you can add water from center pivot irrigations, for example, you can get a tremendous amount of vegetation response and chlorophyll activity. But outside that, it's just a mineral surface, and that's going to have values that are in the lower range of negative values that are less than 0. So here's looking at Castroville, California, in this artichoke area. Here's the NDVI image, and we can see that in the reddish areas, like where my little hand is showing here, are active agriculture. This is an agricultural area, are active agricultural fields with abundant water and plant metabolysis happening. And in these blue areas here, well, these are water bodies, so there's no NDVI, or rather a negative value for NDVI pixels that are bodies of water. So you can kind of see here, low values correspond to buried areas of rock and sand or snow, and below 0, and negative values are generally clouds, water, and snow. As we move up, we get moderate values, 0.2 to 0.3, that represent shrubs and grasslands, and moderately high indicate crops. And then you get some very high values that range as high as, I've never seen any higher than 0.8 myself, but that are used in rainforests, irrigated lawns, and other situations where there's very high plant metabolism going on. Lots and lots of chlorophyll activity. And you can use NDVI. So the power of NDVI is detecting vegetation, but the sensors can do this at any resolution. So here's Landsat data at 10-meter resolution, and it's able to cover these areas many times a year. So we can actually use this as a way of doing spatial temporal analysis. And that's what you're going to do in this lab, is you're going to compare this area of Monterey County in California, the artichoke capital of the world, from August 2013 data to August, September 12th. Let's see. There's a little typo there. Anyway, this September data from 2015, August data from 2013, and generate NDVI polygons, overlay those onto the images. And you can see here, for example, in 2013, this little polygon here and this polygon here were active in agriculture, and here they're more like they have lower NDVI values and have barren ground. And so we can use the satellite imagery bands to detect those changes and conduct spatial temporal change analysis. And here's what the NDVI looks like from those. So so that was looking at the satellite images. These are the same images but processed as NDVI. And again, you can see here how, like, looking at this little oblong shape here, or all of these that are kind of cyan colored are kind of in the 0 range and represent bare soils. The areas, that area in 2015 was actively emitting infrared, very near infrared wavelengths that bring it to the high level of red, sort of like in the 0.7 range of the NDVI scientific. So by making those comparisons, we can generate these polygons and generate change imagery. And many people use NDVI over large areas at low resolution in climate change activities, for example, in monitoring to look where vegetation is stronger or weaker or healthier than it was in a previous time frame. And because the satellites ubiquitously collect very near infrared and red as 2 of their wavelengths, there are many sources of imagery that can be used for NDVI, ranging from 1 kilometer grid cells that conduct analysis of the Earth daily, such as from the SPOT French vegetation system, down to drone imagery with 2-inch resolution that can all do NDVI. And so you're going to learn about that important index as well as some raster technique in this lab.